meeting will be the same as always. So we start with a 40 minutes presentation roughly, followed by a Q&A from the audience, and then ending with the feedback in this discussion section with Carl. And I believe we are recording. That's perfect. Thanks, Carl. So today I am delighted to introduce Tom Ringstrom. Tom received his PhD in computer science from the University of Minnesota. Without further ado, I'll pass it on to you, Tom. Thank you very much for joining us today.
Yeah, thank you very much. Hold on, I'm just trying to give permission to Teams. 1 second.
Yes,
to share my screen.
It's always a bit of a.
It's asking me to quit and reopen, so I will be
okay,
back in a second.
Perfect. We'll wait a second. And this is also just a friendly reminder for everyone that we'll start to publish these recordings, just that you're aware. If there's any problem, let us know. Yeah, but we're obviously still very happy about everyone's engagement despite being recorded. I think Tom is back.
Okay, let's see.
Perfect.
One second.
Yeah, easy.
You see that?
Yes, we can see that perfectly.
Cool. Okay, yeah. So I'll start. Also, let me know if I think you said 40 minutes plus or minus 10 minutes in the email. So I'm starting now. Just let me know if I'm like running low on time.
Yeah, that's all relaxed.
Sure. Yeah, my name is Tom Ringstrom. I got my computer science PhD at the University of Minnesota with Paul Schrader. And I'm going to be telling you a little bit about my work in my thesis. And so the title of this talk is called A Unified Theory of Compositionality, Modularity, and Interpretability in High-Dimensional Planning and Intrinsic Motivation. So the purpose of this talk is to make the argument that sort of standard Bellman equations, used for reinforcement learning, don't really support a lot of the features that you would want out of like flexible adaptive agents. And there are ways of formalizing new forms of Bellman equations that both allow for sort of adaptive, compositional, high-dimensional planning and also intrinsic motivation. And so it might be interesting to this lab too, because it might sort of overlap with some theory and active inference. So we can talk about that later. Anyways, so the overview of the argument is that the world is very dynamic. It's reconfigurable and high dimensional. So we might have internal states like thirst or hunger, like internal, and external states like world states or task states. And so we need to plan within like very high dimensional, in a high dimensional world, and keep track of many variables. And so how might you do this? I'm going to argue that you need to exploit sort of principles of compositionality and modularity and interpretability in the sort of predictive representations that we use for planning. And furthermore, there's another problem, which is how do you know what a good goal state is in a high dimensional space? So the problem, for instance, in reinforcement learning might be that reward functions on like high dimensional state vectors are undetermined, or they're very difficult to sort of rigorously define in a normative sense. And so I'm going to argue that an intrinsic motivation function called empowerment can do this in high dimensional space, provided that you construct the right predictive factorizations for high dimensional planning. And so this will allow us to sort of compute intrinsic motivation over long time horizons in high dimensions. And so in order to do this, we're going to build planning factorizations. And these planning factorizations are going to be called state-time option kernels. I'll talk a little bit more about what an option is and what an option kernel is. And this is going to allow us to sort of chain together skills and justify complex goals. And the way we're going to do this is we're going to formalize a different form of the Bellman equation that will directly optimize these state-time option kernels. Okay. So part one of this talk, we'll just start by talking about these option kernel Bellman equations, and then we'll move on to talking about sort of the high dimensional version of it. So the standard Bellman equation looks like this. So you might be familiar with this. The value function, V, is equal to the reward you get now at a given state in the world, say the state this badger is at, and the action it takes, plus the discounted future rewards that you get in the future. So this is an expectation over the future rewards. Okay, and then, so what happens is when you optimize this value function, you'll get some value function over some discrete or continuous space, and it'll look like this. And the policy is going to select actions that ascend the value function gradient. But there's a problem. So you can't really spend accumulated reward. It's not like a substance. You don't really collect it. It's not a state of the world. And another problem is that important spatiotemporal information is lost when you're maximizing a reward. So for instance, an apple might be available at a tree at a specific time in a specific state. But if you get rewarded for eating an apple at this tree, for instance, that information, spatiotemporal information, isn't used. It's basically lost, essentially. You just care about the reward of eating an apple. And so value functions play a kind of normative role, but they don't play a sort of functional role. They don't really help you plan in like new scenarios. And more importantly, value functions don't really have a high dimensional, they don't have a decomposition over high dimensional transition kernels for instance, a sparse reward problem. So like in a video game, if you want to get to the end of the video game and that's rewarding, well, it's unclear how value functions are supposed to decompose over high dimensional transition kernels. So the new Bellman equations I'm going to introduce sort of, they address these four things that I just mentioned. So these new Bellman equations are called option kernel Bellman equations. And the differences go like this. So we might have a grid world here, and a goal function, fg, is just going to encode the probability that if you're at a state and take an action, that you're achieving a goal. So alpha hydrate here, you can just think of it as a sort of goal satisfaction variable. It's going to have sort of enriched meaning in a few slides, but you can think of it as just a goal indicator. And so if you're at the lake and you drink from the lake, then the goal is just going to be encoded as 1. It can be probabilistic too if you want. Or if you're not at the lake, you're just at some other states, then the goal, this is going to output a 0. So you're not achieving the goal. And you might have a constraint function, which says, which outputs 1 if you're not violating a constraint. Say you're not in the fire at this state, so it outputs 1. And if you're in the fire, then it outputs a 0. So 0s are bad, 1s are good, and 0s are bad. So this new Bellman equation looks like this. Kappa here is going to be a cumulative feasibility function. And so this equation has two functions, an achievement function, which is just the product of the goal function and constraint function. So that's going to output 1 if you're achieving the goal and not violating constraints. So 1 times 1 is going to be 1, and that's you're achieving the task with probability 1 from this state in action. And then we have a F2, which is a continuation function, which is you're not achieving a goal, 1 minus FG, but you are not violating a constraint. So that means you can continue acting into the future. And so then you're also just multiplying by the expected future feasibility. So this feasibility function is just collecting the cumulative probability of achieving a task, which is achieving a goal and not violating constraints. Okay, so usually, the normal Bellman equation, usually the discount factor sort of incentivizes time minimizing policies because you want to get to the reward as fast, so it's not as discounted. But we don't have discount factors here. So what you can do is you can basically just select an action which maximizes the cumulative, but you select from this set A star X, which maximizes the cumulative, but you select it to minimize the goal satisfaction time. Okay, and then I'll tell you what this function is here. This is a state time feasibility function. So eta here is going to be a probability distribution that if you start from state X, so that's here or anywhere in the map, then the final state time that you achieve, this is a probability distribution of the final state times that you achieve a goal, say, drinking from the lake. And so then there's also a state time infeasibility function indicated by a minus here. And this is just the distribution of violating a constraint. So the probability, if you have a stochastic kernel, you might expect that there's some probability mass and some temporal distribution of hitting this fire en route to the lake. And then since this is t minus 1, this is not defined for negative time, so we have a sort of boundary condition at t0, and that is right now you're either achieving the goal or you're not. So this is the achievement function, and this delta is just saying that these states are the same. So you're achieving the goal here and now, or you are not, or you are violating a constraint, which is a failure, or you can't achieve the task. So this indicator function here, is a function of kappa that says the goal is achievable. So kappa is greater than 0, or the task is infeasible, which is also a failure. So if you get disconnected from the goal, you get into part of the state space which is disconnected, that's also failing the task. And the important part here is that we can add these two functions together to create a state time option kernel. And so an option is a concept from reinforcement learning, which is just a pair. It's a policy and a termination function, beta. So the termination function is just going to say, when does the policy terminate? And so those functions are given here, which is also these two, defining these two functions here. So either you achieve the goal, or you violate a constraint, or you don't, or you fail the goal because you can't achieve it at all. And so these termination conditions give rise to a kernel. So this is going to sum to 1 over the final state times. So this is going to say I start from this state here, and then I have a full distribution over state times when I achieve the goal, but also fail it by, say, going into the fire. Okay. Feel free to ask any questions if you have any too, if I need to clarify anything. So we can visualize these Bellman equations. You can solve these Bellman equations just by sort of a cousin of value iteration, just by dynamic programming. And so we'll look at that. So say we have a grid world here with 2 goals, and each goal has 3 states where you can achieve the goal. So these 3 here are goal 2, and this is goal 1 up here. Then we have a constraint function. So these states here are states you don't want to hit. So you have to sort of cross this bridge. And you might have, noisy dynamics. So you might go, forward the correct, direction 80% of the time, but you might, drift to the side or stay in the center with some small probability. Okay, so task 1 looks like this, and task 2 looks like this. If you're to visualize this cumulative feasibility function, it just looks like this. So yellow here is the cumulative probability that you achieve this goal, this task 1. So this is probability 1 here, and then pink here is like 0.5. So you have to go through these constraints and not violate the constraints, and so you lose probability mass. It's like a 50% chance of being able to get to these goals. And same for here if you're coming from this side. And then if we look at task 2, it's sort of the same. If you're close to the goal, then you're going to get there with probability 1. But if you're very far away, it's about 0.25, because you have to cross through these constraints, and then you have to cross through these constraints again. Okay, and so if we look at the policy, we're minimizing the time, so we can just select the action which maximizes this cumulative, but also minimizes the expected time. And so the policy, here's the arrows for the policy dynamics. And so we can also visualize this predictive map, the state-time feasibility function, which says that, if I start, from this state X, so this is like the purple square here or the blue square here, this X plus and T plus is the distribution over final state. So you're most likely to end in the center, for instance, if you follow this policy from this state. But there's some probability mass that you drift off to the side. And then we can look at the infeasibility function. And so this is the sort of probability that you're going to violate a constraint at a particular state under the policy. And of course, before I said that these two functions added together form a full state-time option kernel, which sums to 1. So this just looks like this. And so this is, red and green. If you sum over red and green and the time distributions, which I'm showing here, then all of that sums to 1. Okay. So the meaning of these maps is, if I were to take a one-hot vector that has all of its probability mass on this initial state where this purple is, then the maps say, where is the sort of probability mass going to freeze in the constraint state or the goal state? So this process never happens when we optimize. It's just what these maps mean. We're computing these maps by backwards induction. And so similarly, here's the meaning of the second map. And because these are kernels, transition kernels, they have a nice property, which is that you can compose them. So options, are policies with determination conditions. So you could sequence options, option for goal 1 and then option for goal 2. And we'll just call this row. So row is just going to be, a sequence, an open loop sequence of options, and 1, 2 is just option 1, option 2. And so the composition, we can create a composite transition kernel for option 1, option 2 by this equation. So what you'll notice if you look at this equation, there's a discrete convolution in the time domain here. So there's going to be initial, final time. The end time of following the chain of policies is T row. So which is going to be the probability of ending at some intermediate time TF1 for task 1. And then the remaining time T row minus TF1, there's a probability of this remaining time. And then you sum over all of these times. So that's a discrete convolution. And then you're also marginalizing over the intermediate states. So this is a sort of Chapman-Kolmogorov equation with a convolution in it. And so this just produces a new predictive map for a chain of options. So we can visualize what this looks like. We can compose this map with this map and their time domains to get this map and this time domain. So you can see that this is the final distribution over doing goal 1 to over here, and then going from goal 1 to goal 2. And then you also have the distribution over constraint violations. And so this is getting smaller, of course, because you're losing probability mass, to the constraints. Okay, so you can also just visualize this. This is what this map means. This is the distribution of rolling out the dynamics. Okay, so that's the option kernel Bellman equations for some low-dimensional grid world. And so now we'll just talk about what happens when we have many state spaces that we care about controlling. So we might want to compose transition kernels. So for instance, if I have internal states for hunger, it might look like this. And I might be able to control, so here, being at Y10 is going to mean that I'm fully satiated. And being at Y0 means I'm starving. That's why there's a little skull and crossbones here. And so these alphas here are sort of actions on this space. Either I'm not eating, right, and I can get hungrier over time, or I could eat and I become like fully satiated by eating an apple. So we can sort of couple these two transition kernels. We can have a transition kernel for the low level and this one, and we can couple these through what I'll just call an affordance function. So an affordance function is going to map any state action in the low level, base level space to an alpha, which is a kind of action variable on a higher level space. But this is an action variable that we don't directly optimize. Right, we can only optimize A, but we can set this alpha by a policy in this space. So we can go to the tree and eat and set the alpha here. So these alphas are going to map to eat, and then any of these sort of non-tree states are going to map to this alpha epsilon, which is like the null action. And so the composition of these transition kernels just looks like this. S is just the full state vector. And we just multiply these together and marginalize out alpha to get the full dynamics. And if we have many transition kernels for hunger and thirst or temperature, stuff like this, we have the same story. Okay, so instead, we'll have bold alpha, which is a vector of alphas for all of these spaces. And then bold D is just going to be a vector over each state space for W, Y, and Z. Okay, and then here I'm also adding in a sort of mode function where a mode is just going to condition the possible dynamics on this low level space. So the reason for that is so that if you die, for instance, if you starve or you dehydrate, then this is just going to condition the dynamics on the space. So if you die, you can't move around. This is going to condition sort of defective dynamics where you're essentially dead and you can't move. And then if you're alive, meaning you're not in any of these states, you can just have normal grid world dynamics. So this creates a sort of coupled transition kernel. Okay, so we can sort of build these, factorized transition kernels, but of course, the problem is that you can't really do dynamic programming in high dimensional space. So now I'm just going to talk about how these option kernel Bellman equations can help build factorized representations for planning in high dimensional space. So, like I said, we might want this option kernel that says, oh, I start at this low level state and this configuration of internal states, and that's D, and it maps me, to my a state time vector, a final state time vector. That would be really nice, but in order to get that exactly, you might have to, solve a dynamic programming problem over this entire transition kernel, which is what we're trying to avoid because of the sort of memory problem. But the nice thing about these option kernel Bellman equations is that there is a factorization for them. So as long as certain conditions hold, which I'll talk about in a second, you can factorize this into a base level state time option kernel for moving around low level space times the high level predictions for these state spaces. So omega here is just going to be an initial to a final state transition function given a certain amount of time. So omega d is just going to be this product of individual prediction functions. And so it's just the product of all of these. And so one of these, for instance, is just the prediction that if you start at z, say here, that if, say, 4 time steps elapse, you're going to end up at final state zf. And that is just going to be equal to the Markov dynamics of conditioned on the fact that you're not achieving a goal. So like you're getting colder or you're getting hungrier or thirstier over time. So this is a Markov chain, and we're just taking it to the power TF to evolve this system. So as you can imagine, if you violate a constraint, such as going into the death state, then you can't really finish an option. So the smallest time to constraint violation is set by the sort of minimum time to a constraint violation. So you can compute this. I won't talk about how you can compute this, but if you have an option, for instance, that is going to the lake to drink, then that's just 2 steps away. All right, so that means that if we were to predict the final state of all of these systems, they are going to end up here. And that's fine. We're not violating any constraints. So that's good. But if we go down to the tree, right, that's 5 time steps away. So these 2 state spaces might be fine. We're not violating constraints in these high-level state spaces, but we will enter into the death state for this state space. So that would mean that the option wouldn't finish, and so we can not consider that option. So the conditions are, this factorization holds if the goal function is just a function of the low-level state to a tree or to the house or to the lake. Another assumption, right, is that the state space dynamics are consistent over X, meaning it doesn't matter what trajectory I take to get to the lake, I'm going to get thirstier by the same amount. All I need is the time that it takes to get to the lake. It doesn't matter the path. Okay, so this is nice because we can compute this factorization efficiently, whereas we could not compute this efficiently with dynamic programming. But this is simple to compute and represent. And that's good because now we can basically decompose a problem by solving, for instance, for like 5 individual subgoals where subgoals naturally arise from the connectivity between stuff in the base level space and their influence on other systems through this affordance function that couples the 2 systems together. So for instance, I can solve 5 separate problems and I have 5 separate state time option kernels and policies for them. And that means that for each of these state time option kernels, I can basically couple these with their predictions, and I can define a goal operator that's going to take in an option or a policy, one of 5 policies, and it's going to advance the state vector through this factorization. And the reason for this part right here, it says 1-step boundary action, and this is just for a technical condition, which is some of your options can end on an action. So if you're committed to an action at the end of the option, then you have to evolve the dynamics one step so that you can initiate another option. So this is just a sort of technical condition here. So we can plan with this goal operator using this sort of efficient factorization. So we can sort of visualize what this looks like. So you're a hiker and you're going to go on a little journey. So you're going to go up to the lake first. So you're going to have an initial to final state time prediction from xg1 to xg2, tf1. And that's going to take you 2 time steps down to the lake and then 1 time step after you drink from the lake. And this is the 1-step update. So once you get to the lake, you're going to be here, but you're committed to a final action, which is going to fully hydrate you. And so this function here, omega, is just taking this time, the Markov chain of the dynamics of this space to this power tf, and that defines this brown arrow here. Okay, so we can also update all the other spaces with similar omega functions here. Oops. Okay, so here's our goal operator again, and here are the transitions. So purple here is a state to state time jump, and then these are the brown arrows here for the prediction functions. So we can continue the journey to the tree, and then we can condition the journey back down to the house to get warm. Okay, and so we can also visualize another route. We might go to the tree first, and then we might go to the lake first, or second. And then you'll notice that the lake is very far away from the house, and so this option technically should not be followed because you're going to violate the constraint of hitting a constraint state. And these other state spaces don't have to be like dynamic state spaces, like physiological state spaces. They can also be like logical state spaces. You might have to gather an apple, and then maybe gather some water, and then obtain a key, and you can just register those items, for instance, in a bit vector space. So these other state spaces can be flexible. This is more like an automata, like a task automata. And so we can just sort of visualize some of these problems. These problems can also be non-stationary. I'm not going to talk about sort of non-stationary dynamics in this talk, but essentially the obstacles in the world can also be non-stationary. So this is achieve all 4 goals before they disappear in order to satisfy the task. And so you can forward sample a solution through this factorization. You optimize over the space of chains of options. And here we have a similar sort of non-Markovian, non-stationary problem where the agent can also open these red doors by hitting the yellow buttons. So the agent can also sort of change the structure of the environment as well. So these would be very difficult planning problems with any sort of normal infinite horizon Bellman equation or A star, just due to their dimensionality and complexity. But these are possible because the optimizer is basically is not considering any of these sort of gray states. It's just optimizing over these final states for yellow and green states. So we can sort of look in the optimizer and see what it looks like when we're solving one of these problems. So let's say that I have a task where this badger has to gather honey and flowers and bring it to his friend up here. And so you also need a key in order to go through this door. So if you have the key, it's going to change the structure of the environment. And you also have to stay alive. So this state space up here is the hydration space, where this is the death states and this is the fully hydrated state. So we can sort of forward sample. So what we're going to view here is one branch of a breadth first search over options. So this is like tree search over chains of options. And we're just going to look at one sort of branch in this tree that's like a successful plan. So we can go to the lake, and that's if the transition kernel is noisy, we're going to have some distribution over time that it takes to get to the lake, and that's going to be expressed. You're going to be able to see this in the sort of dispersion of probability mass from the initial to final state distribution in the high-level space. So then we might go down to get the key from the sleeping bear, and so some of the probability mass is going to hit this fire if there's noise in the low-level transition kernel here. And so this red probability mass here corresponds to freezing at this state, given that there's noise in the kernel. I'm going to take away this red probability mass because it'll get confusing if I left it in. So I'm going to subtract this off of all future updates. So now that I'm here, you might go back to the lake to drink, right? So you're going to end here, and oh, by the way, the one-step update, like after I drink, is going to be the change from here to here. So once you get to the lake, this probability mass is going to map up to here. But some of the probability mass is in the constraint violating death state, and I'm subtracting that off, so that's not going to show up. Okay, so now I might go to pick up this item. So I collect the honey. So that's now registering in a bit here. I go back to the lake, and then I go to the flowers to pick up this item, and then I go back to the lake, right? And this is just updating here, and then go to the final goal state of taking these items to my friend here. So we can basically explicitly compute, the probability of satisfying this task in high dimensional spaces, even with like noisy transition kernels. And so that's very useful. That's like, this means that this framework is sort of good for verification. For instance, in AI safety, you want to know what's the probability that I'm violating constraints, what's the probability that I'm achieving goals, et cetera. This is all very useful for like doing sort of like risk sensitive planning and things like this. It's important to sort of take a step back and think and reflect on the fact that, in reinforcement learning, you don't get this interpretability, right? The value function or the Q function doesn't actually tell you what events are going to happen, right? All of that information is just gone. So yeah, that's the final state. Okay, so that's sort of verifiable high dimensional planning over chains of options. And so now I'm just going to talk a little bit with the remaining time. I'm going to talk about intrinsic motivation. So we talked about instrumental planning in high dimensional space over chains of options to achieve a specific state. But how do you know a particular state is good? And so I'm going to talk about this function, empowerment. So empowerment is formally the channel capacity of a transition kernel, given that you start in a particular state, so xt. And it's the channel capacity between sequences of actions. So A here is a random variable over the space of sequences of actions, where the sequence is of length n. So we have a hyperparameter here that sets the sort of horizon of empowerment, and t to tau minus 1 is basically the time duration of this sequence of actions. And then big X here is a random variable over final states. So the channel capacity is formally the maximum mutual information between sequences of actions and the resulting states. So you're looking for the input distribution over the space of sequences of actions. Mutual information is defined as the entropy, the final state entropy, minus the final state entropy, given that you know the action sequence. So it's like how much can I do minus how much can I do given that my knowledge of the actions. So basically, this, for instance, if you apply this to like a double pendulum, an empowerment seeking controller will stand straight up because this is a more highly empowered state. Basically, the controller has a much better control over the range of possible futures from this state as opposed to a state down here. And so there's two extremes of empowerment. There's action independence. So for instance, if your transition kernel has future state probabilities that are independent of actions. So say every action you take is like a uniform distribution over next states. Your actions aren't discernible. Well, then your conditional entropy is going to be the same as the entropy. It doesn't help to know what the actions are. And so in this case, if you substitute this in for here, then you have this entropy minus itself, and that's just going to be 0. So even though you could, if this is your initial state, even though you could reach all of these states in pink, you have no control over which state that is. So that's not empowered. And then the other extreme is with determinism. So if you have determinism, then you have sharp distributions over next states. And so the conditional entropy of a future state, given actions, is going to be 0. It's going to be a sharp. And so that means you can plug in 0 here, and your empowerment is just going to be the maximum possible final state entropy, which in information theory, a simple result is that this is just the logarithm of the support of the distribution, meaning just the logarithm of possible reachable states. So the same situation here, we have an initial state xt here. All of the pink are possible reachable states under a chain of 2 actions. And so the empowerment for horizon 2 is just log 13. Okay, so we can compute empowerment over an entire state space at different horizons. Here, so red here are walls. So that's going to sort of define the boundaries of the world. A here is highly empowered at a horizon of 1 because there are 5 assuming determinism, there are 5 possible states. And B here, it has low empowerment because it's sort of boxed in by these walls, which limit the sort of possible next states. So there's only 2 possible next states here. So the empowerment is log 2. But at longer time scales, the situation reverses. Here over a horizon of 5, you're sort of trapped in this room. So there's only 9 possible states you can reach. But here in B, you can actually sort of spill out into this open area. So this is sort of higher empowerment, higher empowerment than A. So black is high empowerment. And so, here we're talking about flat empowerment. But, the problem is that if we conceive of, agents as being collections of many different systems, hunger, thirst, task states, etc., then you have to be able to apply empowerment to like the full Cartesian product space. And so PS here, which is like the fine-grained kernel for the entire system, you can't really compute empowerment at long time horizons because of single actions, because that's going to limit the range at which information can sort of propagate across your kernel, right? However, we built this factorization G, which instead of low-level actions, we have options as actions, which map us from initial to final state vectors. And so that means because G is a transition kernel, and empowerment is a function of transition kernels, we can actually just apply empowerment to the factorization for moving around high-dimensional space. So that's empowerment. And so now I'm just going to talk about, well, what if you just maximize empowerment gain, like the change in empowerment in high-dimensional space? So valence. So empowerment has two arguments: the state and the operator, transition kernel P. So any change in either of these arguments is going to induce a difference in empowerment. And so you might have some initial state vector here and some initial empowerment from of the world model, and then you might control a chain of options into the future and get a final state S row after you finish that chain of options. And there can be a gain in high dimensional empowerment over this chain of options. And so we're going to call this valence, which can be, you know, a positive gain in empowerment or a negative gain in empowerment. Okay, so we can think about computing this over, you know, high dimensional transition kernels in this scenario. So for instance, in one scenario here, we have a world with a transition kernel that doesn't allow us to go through this mountain pass. So if we don't have a key, we can't get through this mountain pass. So that means if we're on this side, we can only drink from the lake. But if we had a key, which we're going to represent with this variable phi, then we can pass through this mountain pass. And so that means that we can sort of traverse, you know, from this side to the other side. And so that'll be phi 1, meaning we have the key. And so this means that we can have different transition kernels conditioned on having the key or not having the key. E1 here is just going to be mean the environment that is like a variable conditioning the transition kernel, which is basically just shorthand for having the key. So we could have a factorization for G. We could, for instance, build G so that we, you know, optimize an option to the lake and also to the tree. And so this would be without the key. But we also might have, you know, one for this environment where it's open. So we can build a goal kernel conditioned on this being open. And so we can compute, you know, the difference in terms that due to, you know, opening the door, being able to open the door with the key. So what does that look like? Well, if you're constructing a plan to go get the key, you might have an initial empowerment. So pink squares here is low-level empowerment, but we also have task empowerment, which is pink circles. So there's really only one task you can do, which is drink from the lake, and that's good. So you're going to have an empowerment of 0 in task space, basically. But if you go up and get the key, that's going to transform your internal vector down to here. But you also condition a new dynamics mode that allows you to go through the mountain pass. And then you can go back and drink from the lake, and that's going to bring you up to here and also map you down to here. But now the difference, of course, is that you can move through the door. So there's an expansion of empowerment just in the low-level space. But of course, what really matters is that there's also an expansion of empowerment in task space. So it means that we can sort of hop between the tree and the lake as many times as we want to stay alive, and that's going to sort of show up in this empowerment. So at a horizon of 3, the task empowerment is log 8, because there are 8 possible sort of branches of a tree of like drinking, then eating, then drinking, or drinking, then eating, for instance. So empowerment in task space is going to be log 8. And so that means that there's going to be a positive fine-grained valence and a positive task valence. And so this means that we can answer very interesting questions, which is like, what is the value of the key? Like, independent of the plan to go get it, we could even compute just like, given I'm at this state and I just modulate whether I have the key or not, like I change phi0 to phi1, you can basically say that the key's value is a kind of credit assignment. It's giving, it's responsible for, changing the empowerment, everything else constant. And so that means that value can come from changes to the sort of agent environment coupling. And that concludes my talk. I think I'm running out of time, so I'll just wrap up and sort of walk backwards. I argued that we can compute intrinsic motivation in high dimensional spaces by computing this empowerment gain, which requires us to be able to compute our empowerment in high dimensions. And so this helps us make sort of contextual value judgments, without reference to some other reward function or value function or something like that. And this is only possible because we have factorized planning representations that we can represent. And this allows us to sort of plan over high dimensional worlds. And this is possible because we have Bellman equations that save all the spatial temporal information and build the transition kernels. And so with that, I'll wrap up saying, this allows us to plan in dynamic product spaces. I basically just said all this. So STOKs are compositional, factorizable, and interpretable. And we can basically solve for many of them to create a goal kernel. And the valence of these goal kernels can be used to justify goals and constraints. And so even if we have many possible drives, we can sort of unify these into a sort of single value. Okay, so thank you. And I'd be happy to take questions. Thank you for listening.
Thank you very much, Tom, for this fantastic talk. Very interesting. Quick unmute everyone and a round of applause. And please go ahead and ask questions if you have any. Yes, Polly, please.
Yeah, I'm interested in to what extent you've thought about how, with this particular kind of factorization, how you might be able to learn in these systems, because I mean, it's like clearly these representations are really powerful when it comes to solving these complex high-dimensional problems. But the immediate issue I see here is like, how do you ensure that you're learning, that you can learn these particular factorizations in such a structured way?
Yeah, it's a great question. Yeah, like a lot of this is just, the model-based theory, right? And, my answer is that I think we just need better theory for creating task-agnostic sort of dynamics models of the world. How do we, for instance, if you wanted to apply this to, an Atari game or something like that, how do we build the right kinds of factorizations so that we can, for instance, do like latent space control? I guess, what I would say is that the sort of standard bag of tricks of reinforcement learning where you like parameterize RNNs and Q functions by neural networks, I would say that this isn't going to work. And essentially, we just need better theory for like building better world models. Does that answer your question, or would you like me to expand on anything else?
I mean, no, yeah, great. Thanks, and thanks for the talk. Very interesting.
Any more questions for now? Maybe also, Tom, if you have specific points which you would like to get feedback on from the audience, or Carl, you can maybe talk about these. If you have.
Yeah, specific points. I guess, I think, the reason I'm sort of all on board with this framework and idea is because I think that it's going to be very difficult to make agents that can make sort of on-the-fly value judgments in a sort of open-ended world. Like, how do you make agents that not only learn the structure of the world, but can also make value judgments about it, right? And I think, the problem with reinforcement learning is that it makes a sort of promissory note. It says like, oh, we're going to maximize the amount of reward, and we're going to make commitments to certain functions like value Q functions. But we don't know where the reward comes from, but we'll get back to that later eventually. But now we'll just, do instrumental planning and so on and so forth. And I think, the point I'm making is that, like, just to do instrumental planning, I think you need these kinds of factorizations, right? And that's just instrumental planning in like high dimensional space. And, I'm saying like this only arises because you sort of get rid of reward maximization, because reward maximization sort of leads to uninterpretable, sort of non-composable functions. And so, but by, getting rid of this and actually building these factorizations, it makes intrinsic motivation possible. And so I guess the reason I think this is important is because it means that you never have to represent something like a high dimensional Q function or something like that. Because empowerment gain is essentially just sort of implicitly accumulated in the structure of the agent itself. Like if I do some complex task and I change my state vector of the world, or I also, change the structure of the transition kernel, well, that defines me. Well, that's now, that's when I make decisions from there out into the future, I'm just making it, with respect to, the structure of what I am paired with the state of the world. So you never really have to commit to these kinds of representations that RL makes you commit to, which I think is very important for thinking about, open-endedness. How do we have a theory of open-endedness? Does that make sense?
Yes. Yeah, I guess so. Very interesting. I mean, if someone from the audience has something to say to this now, otherwise I'm sure I will pick up on this later. And also I'll just leave a minute for any other questions to bubble up. Maybe I can just come in with a question. I'm not sure whether I might have missed something, but I'm just wondering about sort of the prioritization of the agent. I mean, in the model, if I understood correctly, it has to do with empowerment, but also, I guess, the avoidance or the distance to constraints. I wonder, but at the moment in your model, I don't think the goals have different values or weights in themselves, right? Would that be a thing that could be extended in this model? Because I think these would be natural things in a way.
Yeah. So I have these option kernel Bellman equations, and they're maximizing the probability of task satisfaction, right? And the point you're making is that when I do that, these goal states in this fact, if for this option kernel Bellman equation optimization, they aren't weighted. But I'm saying that once you optimize those, then you can sort of retroactively compute the value of the goals. So you can weight tasks by utility functions if you want, but also intrinsically by their empowerment gain, right? Because these state time option kernels are predictive maps. So you just take the expected empowerment gain. Are you wondering whether you can sort of prioritize goals in the option kernel Bellman equation itself?
Yeah, I guess so. Or I mean, like in the grid world example, the goals have equal weight, right? Water or food, drinking or food. I guess it was like task prioritization was defined by the distance from the constraint of, I don't know, like dehydration or starvation. So I'm just wondering, like, apart from that sort of like considering the constraint goals had different values, whether that would fit into this model.
Yeah, it does, but not at the level of like producing the predictive representations itself, right? So like, the goal of, going to the tree to eat, well, that can be contextually dependent on a variety of other, spaces in the agent's, full product space. So empowerment sort of does this implicit weighting because there isn't like a way to empowerment in this high dimensional space is just a scalar value. So it's basically incorporating all of these types of constraints. So you do get prioritization naturally from it.
Mm-hmm. Yeah, that's also what I was thinking as I thought more about it. It feels implicitly baked into it. Then one thing did come to my head, like if there are more nuanced goals, like ones that are less about survival. But I guess, so I don't know, I couldn't really figure out how that would fit in, but that's also something that I guess I came to, that it feels implicitly baked into the empowerment, at least with quite clear constraints that are about survival.
Right. So say you're fully satiated and you always have a power bar on you or like a water bottle. And there's never some threat of starving or dehydrating or whatever. Yeah, you can. Other things can be disempowering but not kill you. For instance, like losing your job, for instance. Well, now you don't have a source of income, and a bunch of your other skills are also shut down. Right. So it's a contraction, over the space of other systems that you can influence, that you have habits for, that you have, plan representations for, or skill representations for. And so that can shut down, but it doesn't kill you, right?
Mm. Yeah. Okay, thank you. Do we have any more questions for now? Otherwise, I believe it is your turn now, Carl.
Good. Is it my turn now then?
I think it is.
Well, that was most impressive. How long have you been doing this, Tom?
So yeah, this option kernel Bellman equation, I started figuring out the basic ideas for this around 2021, I think. And it took me a few years to get all of the details right, but we're done with that now.
Good. So have you submitted the thesis now? Is that?
Oh yeah, the thesis is submitted. The presentation today was basically incorporating some things that were missing from my thesis. I made certain assumptions in my thesis about determinism, and I didn't incorporate the options framework formally. So there were just some like missing things that I wanted to do before I submitted this for a publication.
Right, so there will be a series of publications developing the key points as you resolve them. Excellent. Well, I repeat, that was both in your motivation for the specific components going up the ladder and down the ladder in 5 steps, and in response to the questions, this notion of having an open-ended, plausible calculus for making the right decisions and behaving in the right way, I think in a semi-Markovian way, is absolutely right. And identifying the fallacy of reinforcement learning, that is just not expressive enough to handle these things. And so that aligns almost exactly with one way of selling active inference as another way of thinking about sentient behavior or optimal decision making under uncertainty. So part of the reason I'm impressed is that you managed to identify these sort of contrarian questions in the face of current enthusiasm for backprop and RL and the like.
Right.
It can't have been easy given you were a PhD student, but I think you're absolutely pointing in the right direction. A lot of the things you said resonate very much with the work within the space of active inference specifically, but actually also more generally the free energy principle, which is if you like, a physicist take on these issues, as opposed to a sort of machine learning AI behaviorist or optimization take. Some bits I hadn't come across before, which is interesting. So, for example, having explicit distributions over the time to an absorbing state, for example, and
Right.
Actually having the sort of the densities over the path length as opposed to the actual path itself. So there's not much that I think we can teach you. What I will do though is enable you to appeal to related and aligned objectives within the free energy principle and active inference literature that would at least lend moral support and at best provide you with a provable backdrop for some of the assertions that you've been making. So one thing which you could, if you can join the dots, say, between intrinsic motivation in robotics in the spirit of Audier and intrinsic motivation in the spirit of Daniel Polanyi in empowerment, with intrinsic motivation in active inference, which is effectively a kind of mutual information, but slightly more general than the mutual information between the action space and the policy space and the in your instance the terminal or the end point of a particular path. So in my world, the intrinsic value or the intrinsic motivation is part of the expected free energy, which is just resolving uncertainty about the environment, as opposed to maximizing the mutual information between my actions and the environment. But there is a special case if you make a simplifying assumption, the two reduce to the same thing. So I think there's lots of interesting dots to be joined, perhaps just in discussion, as opposed to a formal appendix showing that this is equal to that or this is a special case of that. The motivation, I think, for you though, I repeat, is that unlike many approaches in engineering, the active inference is a consequence of the free energy principle, which basically turns the problem on its head and says that we have a particular finite state machine or a non-Markovian process, or in continuous state spaces, some kind of stochastic chaos with an attracting set of states that my little agent goes through, and I can define those that attracting set in terms of points it must pass through, and these would be the goal states, for example, and also in terms of states that it never visits, and these would be the constraint states or the punishment states that distinguish between your eta pluses and minuses. So what the physics perspective says, well, look, if this kind of object exists, if there is a process that has these dynamics, but also has this kind of technically what is called a pullback attractor, what is a probability distribution over its paths or actions or choices, cast in terms of probability distributions or uncertainty. And then what happens is, what falls out from that is exactly the mixture, well, nearly exactly the mixture of this intrinsic motivation and the way that you formulated the goals and the constraints in terms of various outcomes. So in terms of being in a particular part of state space, but the consequences of that in terms of observations or outcomes that will ensue from those latent observations. And that basically means the form, having all the different bits that you've brought to the table has to be correct from the point of view of, if these kinds of agents exist, this is exactly the kind of objective functionals it will look as if they are optimizing. So that's that's, if you like, the what the free energy principle will bring to these arguments, which, I repeat, it's not so much what are the objective functions that lead to a particular attracting set of characteristic states of an agent with goals and multiple operating under multiple constraints, but if such an agent or system existed, what kind of functionals would it look as if it was optimizing? What I'm going to do with your permission is, if I take the if I share my screen, I've just got about 3 or 4 papers that, should you want to, you can go to and just try and see if you can transcribe your maths and semantics onto, in part. It won't be a perfect fit, but it will be, I think, that satisfying partial fit that would provide you with the discussion material to say that this is consistent with the physics of self-organization, and notice that it's not the same kind of thing you'd read in a Bayesian RL paper or deep RL paper. So if I can,
sure, yeah, that'd be great.
Okay, then. So
I think you need to stop sharing your screen, Tom, so that Carl can take it. Perfect, thanks.
Right. Oh, right. Good. Okay. Yeah. So I'm going to go through this very quickly because I'm aware this is being recorded. So if you're interested, you can go back and read through at your own pace. I'm just going to give you the sort of conceptual links that might be of interest for you. This is very high level. So what I'm doing here is picking up on this key quantity that underwrites most of active inference, certainly as implemented in non-Markovian decision processes or MDPs that are stacked in exactly the way that you were describing, to equip them with a certain kind of depth that breaks the Markovian properties of a single one. And this expected free energy can be expressed in terms of the negative log probability, i.e. the energy of a particular action or policy or path. I think you were denoting by capital A. You can derive in terms of probabilities over latent states and actions what this must look like. And one of the key compositions which I think is going to be pertinent for you is that you can rewrite this as an expected cost plus an expected information gain, which is formally what I'm reading the empowerment mutual information as a relative entropy, as a KL divergence, as an information gain afforded, and you express that in terms of the sort of the difference between the can't remember now what you called it, the child capacity with and without this particular move. So that would be a gain in the mutual information. I say it's not quite the same, and that's why I'm introducing this paper first. But my point here is that this doesn't require any heuristics or theorizing or reinforcement learning or behavioral psychology or machine learning. It is just a truism that inherits from the existence of any system that has this kind of pullback attractor. And by any system, I'm now talking about systems not written in terms of discrete state spaces, but in terms of Langevin equations and continuous dynamics. So the equivalent here would be stochastic chaos within a tracting set. But it is easy, I think, to sort of transcribe that to the discrete state cases that you have been dealing with. So you just start off with where all physics starts, which is a Langevin equation, and carefully working through, you end up with this decomposition that is, I think, provides a first principle motivation for saying that just talking about expected cost is not sufficient. There is some kind of information gain that you have to put in to describe open-ended adaptive systems that seem to self-organize, have this kind of generalized homeostasis, and respond adaptively in the face of in real world and capricious environments. Sorry, yeah, I should have. So this is a summary, the most recent summary of the free energy principle, called Path Integrals, Particular Kind and Strange Things. And you can find out. The strange is actually quite important because it speaks to the itinerancy you get and exactly what you were aiming for in terms of going to the lake, then going to the house, then going back to the lake, then going and finding your badger friend, back to, so what you're talking about is now not just a la reinforcement learning, getting to the goal and then you go home and have a cup of tea. It's how you describe the dynamics of a real world system, that once the goal has been achieved, what do you do next? You go on to the next goal. What is the goal? In what dimension, what state does it live in? So that's the background, the backstory from the point of view of physics. I think you need to link that with empowerment to tell your story. And I'm sure Daniel Polanyi and all his friends will be delighted that you're focusing on that. And I think that is a perfectly good thing to think about. And the way that I would do that is to go to the appendix in this paper, where this paper is called Sophisticated Inference. And in the appendix, it describes how you can get from that generic expected free energy lemma to empowerment, and also, my apologies, here we are, to empowerment under some particular assumptions. So what I'm saying is that there is, in principle, there's a slight heuristic proof in these derivations, but I'm hoping no one will really notice. You can, with this section here, you can now read the expected information gain that must supplement expected cost or constraints of a multiple dimensional sort to empowerment explicitly, as read when it was formulated at the time that this paper was written. The definitions of empowerment have changed subtly over the years. I like yours because it's very clear. It's just the mutual information between my path and the endpoint.
Yeah. So does this empowerment here, is this just mutual information, or is it a channel like the maximum mutual information?
I think well, this was basically based upon I can't pronounce it, but Kleibubin et al. So empowerment a la 2005, where you're aiming to maximize the mutual information between the policies pi and the outcomes at some point in the future, conditioned upon what you've observed of the environment. So I'm pretty sure it will, if it's not formally identical, it will be at least in the same spirit as your 21st century. Well, no, this is 21st century, but your 2025 version of empowerment. What I remember here, though, there was a yes, that's right. There's in the old days, and I don't know if it's true for your formulation, which may have resolved it. There's always an uncomfortable little temperature or precision term in these equations, which holds a lot of secrets. And much of this analysis is really understanding what special constraints do you have to put in play in order for this beta to satisfy the constraints, say non-negativity and the like, and also what implications does it have? Because from the point of view of the free energy principle, the idea is to make moves that resolve all uncertainty in terms of maximizing information gain about everything, including action.
Right. Right. Yeah. So when it comes to empowerment, you can only compute empowerment on the structure of the transition kernel that you currently understand. So when it comes to information seeking stuff, like I want to learn something about it, the transition dynamics of the world or something like that, I can imagine that these equations could have something interesting to say about that, because or that there's like a sort of expected empowerment gain, for instance, that if I press this button to see what happens, then that's going to update my knowledge of the transition kernel, which thereby updates my empowerment estimate.
Yeah, absolutely. Yeah, I mean, that's spot on. And the maths is actually quite surprisingly simple, because in these discrete state space generative models, you basically encode the transition kernels or the probability transition tensors in terms of Dirichlet distribution. So you're just basically bean counting by adding Dirichlet counts. And what you can do is you can work out, well, if I moved over there, what would I see? So you use a posterior predictive density over the outcomes. And then you can work out the expected change in the Dirichlet distributions that constitute both the likelihood mappings and also the transition kernels. And then you can evaluate in a very simple way the expected information again on that. So you're absolutely right. In a sense, I suspect you've got part of that already, because if you've actually got the change in the mutual information, it's just that it's just the mutual information pertaining to the action as opposed to the everything. When I say everything, I mean both the latent states of the environment. So where is the goal, for example, but also the parameters, the parameters of the transition kernels that are the Dirichlet counts in the probability transition matrix. So you can write down an empowerment-like information gain term for all of these things, which just measure the reduction in uncertainty or the KL divergence with and without what you would see if you made this move. And that
Right.
So very often we talk about sort of expected information gain about parameters, and very often they are, well, actually more usually the parameters of a likelihood mapping, but they also pertain to the transition dynamics as well. So that's absolutely right. But in terms of telling your story, my point here was more that this information gain has to be part of a full story about open systems, literally in a physicist point of view, open to the environment and reciprocal exchange from the environment, but also sort of open in the sense that that you meant when you were answering, I think, Poppy's question, or you have to make decisions under all sorts of uncertainty in a very open factorial way. I'm sorry, I can't remember the technical details, but I do remember worrying a lot about beta. Not so much for empowerment, but what this appendix does, it just takes the free energy principles focus on expected free energy, which you can read as basically expected utility, but where utility has both these constraint parts and information gain parts. So you can also read expected free energy as expected information gain minus expected cost, for example. And this goes through the motivation, or one motivation for the expected free energy, where the free energy is in and of itself just the elbows, the evidence lower bound, the marginal bound on the likelihood of your generative model, and then unpacks it in relation to other perspectives So the physicist's perspective would be this non-equilibrium steady state or pullback attractor, which is exactly your itinerant wandering amongst I was going to say rewarding, but I shouldn't, sort of states that allow you to bring yourself back into your attracting set, your characteristic set, your homeostatic states, and stop you being thirsty, stop you being cold, and stop you being this and that. So that would be how a physicist describes it. It's basically a steady state solution that has this itinerary when you're open to the environment, hence the non-equilibrium. If you're closed from your environment, then you just have an equilibrium steady state, and that would be if you like, standard physics that you did at school. But then it goes on to sort of say, well, how can you recover things that work in the literature from this physics perspective? And empowerment is the first in this list. But also something called the information bottleneck. So I don't know if Daniel Polanyi, who was the architect of empowerment, was very close friends with Tali Tishby, who was the author of the information bottleneck approach. I think Tali passed a few years ago, but at one point we used to work quite closely, and with a number of related colleagues, people like Gavin Crooks and Suzanne Still, predictive information and the thermodynamics of that. So it is no surprise that you can take an empowerment perspective, but you can also take an information bottleneck perspective on on the ensuing paths that you choose.
Yeah, I remember that Polanyi also had quite a while ago. He had an information bottleneck version of empowerment. I can't remember the co-author though.
Well, I'm pretty sure it'll have been Tali Tishby. Yeah, because they worked together quite closely for a couple of years, and I can just imagine them writing a sort of information bottleneck version of empowerment. But they both feature this funny beta, which. Which for the information bottleneck, you've got a lot. You can tune that and you can wiggle it around, which to my mind is for as a physicist, I don't find that attractive. But right. They clearly did. And then the physicist comes back with the self-organization. I think that was it. Yeah. Okay. But so here's one of these nice information theoretic diagrams that you could read in terms of channel capacity and the different pressures on information, the mutual information or the relative to the conditional informations and entropies that you were discussing, written from the point of view of, so where's, here we are, yeah. So this might be a useful heuristic if you wanted to just try and situate the empowerment reading of intrinsic motivation relative to the information bottleneck, or the more generic sort of expected information gains about everything. There are also some really interesting links with something that was developed in the 1950s, which is the principle of optimal Bayesian experimental design. So this, if you remember your simulation where you were in a better position if you'd acquired your key, because you could now open the door and test hypotheses about what was behind that mountain range. So in a sense, that is exactly the problem faced by a scientist designing an experiment. What moves do I need to make? How do I need to design my experiment in order to disclose the kind of information that will allow me to resolve uncertainty about what is behind this door? So what is, the good experiment now becomes the key to this door, so I can see what's behind this door. I can test my hypotheses. So that became, if you like, formalized in terms of the principles of optimal experimental design that were exactly, well, not quite empowerment, but it was exactly the expected information gain conditioned upon this policy or this experimental design. Subsequently, re-emerged machine learning in the form of active learning. David McKay did quite a lot about this. If I've got limited data and I have to actively sample the next data point, in order to resolve my uncertainty, say about some parameters of some curve fitting, where would I choose that data point to maximally minimize my uncertainty or maximize the information gain? So this is all in the future. It's all about the change in mutual information that would happen given what I currently know about the way in which the data are generated. So some really nice stories to tell there in terms of empowerment and Bayesian design and the like. So the other reason I put this paper up is that it effectively provides a way of incorporating the empowerment and the expected costs or constraints of the kind that you've been working with into a Bellman recursive-like scheme. But crucially, you're not working with cost functions and the like. You're working with functionals. That means you can include the empowerment in the recursion by dealing with functionals of probability distributions. But it has the same look and feel of a Bellman recursion, but now not in terms of states, but probability distributions over states that depend upon the way that you sample your environment. So this may or may not be interesting, and I just mentioned this, the offering in this paper, simply because you started with the Bellman recursion or the Bellman optimality principle, and then you later described why it's not going to work for you. One way of not upsetting Bellman, although I'm sure he's probably dead by now, would be to say we can use his kind of recursive insight, but now apply it where we need to apply it, which is not states but beliefs about states, states represented under uncertainty, and furthermore states that I can change by acting upon the world, but we can still go back and recover it. So is it an example?
I do think that there is a lot to think about in terms of like sort of POMDP versions of what I presented, which I haven't really attempted, but I think that's that would be relevant.
Okay. Yeah, well, I mean, I read what you presented as exactly POMDP. No, I mean, the maths equations you wrote down were just transition dynamics over discrete state spaces. And all your graphics were exactly, for example, well, before I forget, let me just make the point. One thing which I found really quite important, and something which, if you haven't already foregrounded, I think you should, was this very careful distinction at the beginning between constraints, like punishments, for example, or things that I should not be dead. Yeah.
Right.
And goals. Right. And one thing which I've never seen really sort of formalized or celebrated or said very, very clearly in the reinforcement learning literature is that punishments and rewards have very, very different aspects to them and have to be incorporated into the right, using the right calculus, which I thought you were actually using. I could have read you talking about sort of Markov processes or trains with absorbing states, or I could have read you talking about stochastic chaos, or I could have read you talking about partially observed Markov decision process. The maths is identical. But anyway, come back to that fundamental point, which if you haven't already, I think you really want to sort of keep emphasizing. So the constraints on the paths I choose to take through my continuous or discrete state space are always in play. Right. Whereas the goals are sparsely deployed points or states that I will have to pass through. So they only pertain to the end of a path, but the path itself has to be constrained all the time by the punishments.
Right. Yeah, and if I could add something to that too, I think just thinking intuitively about life, and the fact that we sort of have to cultivate our own values in terms of like what constraints I respect or what goals are relevant. Part of the problem is that, we need a mechanism for value creation, right, which is prior to utility theory. And so I think the constraint view is important because we can essentially get by, remembering that things are constraints because they are, for instance, negatively disempowering. They have a negative empowerment gain. And so we just bake that into everything we do. We don't want to keep, recomputing the empowerment gain of doing something, of violating a constraint. But of course, because the world is so complicated and dynamic, sometimes we have to revise whether, well, maybe in this specific circumstance, I should, violate this constraint. It wouldn't be such a big deal. So I think, yeah, a lot of RL, for instance, just can't really handle this. But it's worth thinking about, how constraints and goals are just open to revision in this open-ended way.
And just pursuing that theme, having constraints implicitly specified probabilistically, even if you don't explicitly have them, but you're implicit in the fact that you're multiplying by probability distributions, I think is another really important point, because you just made that point. There are certain times I'm going to need to violate constraints in order to satisfy another more precisely held constraint. So I'm going to suffer a bit of thirst if it precludes me from being hypoglycemic or dying, for example.
Right.
So, and that speaks now to something which you were foregrounding in the presentation, which is the fact you've got a multiple constraint satisfaction problem at hand here. And to have that, to contextualize one constraint in relation to another constraint can only be done in terms of the joint distribution over the violations, as it were. And having the machinery to be able to specify the relative precision and possibly state-dependent or context-dependent precision of a particular constraint. So, for example, if I am very thirsty, I may have very precise beliefs about getting more thirsty or more dehydrated. Whereas if I'm not, then I may have less precise beliefs. So having the machinery to specify your constraints probabilistically that also have the attribute not just of your preferred states, but also the dispersion or the entropy over which your preferences are specified, I think becomes really crucial, because only then can you sort of prioritize. Again, you discuss this explicitly. How do you prioritize doing this and then that and then that? Well, it all depends upon the degree to which you're violating your constraints. But it is a matter of degree, and it's a matter of degree which is multidimensional. So I can't remember, but I had assumed that you do exactly what active inference does, which is basically write down a constraint in terms of a self-information or a negative log probability that I will observe this outcome or be in this state. So that constraints are just basically written down in terms of a Lagrangian or a potential that just tells you how surprising it would be to experience this outcome. And then hard constraints are, I've got to have this outcome, and with a self-information of, say, minus 32, everything else is completely implausible for me. I'd be dead. Or, no, I prefer this, but, these other outcomes could just have a difference in log probability, log odds ratio of, say, 2 or 3. And that gives you now a space where you can now sort of trade off different constraints. And of course, you just don't have that in reinforcement learning. It's just, but I'd also argue, and I'm arguing here not so much from sort of machine Bayesian RL, or deeper RL, but from behavioral psychology, because there's a lot of discussion both in behavioral psychology and economics about the asymmetries between positive and negative reward, or punishments and rewards. And you get things like prospect theory, from purely economic theory, which I think is, very much a misdirection, because the role of constraints is not the sparse specification of once in a while I'm going to have to eat, or I'm going to have to have a birthday, and it doesn't matter how I get there. As long as I avoid all the constraints en route, so the pathological of my constraints, my punishments are satisfied, I can now do my dynamic programming or my sort of forward-backward schemes and just work out the final goal point, the end point, over which you had your sort of transit times to. So to my mind, what you were talking about was in terms of separating the plus and the minus, or the punishment and the reward, or the constraints and the goals, was very important, more important than, I think, than just saying there are multiple dimensions to constraints. The way that they were implemented, having to avoid en route dying. So dying is not negative punishment, negative reward. You have to be alive to get your reward.
Exactly.
Yeah.
That's the trouble with RL, isn't it? You can't make a negative infinity reward because it corrupts your value functions, and if it's just arbitrarily negative, you can always overcome it with some positive reward or whatever.
Yeah.
So I mean, it's just, you can't express these things. And
absolutely, yeah. And I think that sort of, you need a more expressive calculus of behavior and self-organization. You should really make that, make that a centerpiece as why you are not committing your young life to reinforcement learning and trying to find a better way forward. That's, okay, yeah, sorry. So yeah, this was just an expression of this G, which is very similar to your G, that has but has a Bellman-esque aspect to it, but does actually incorporate the information gain, because it's really a recursion of the sufficient statistics of belief distributions over various quantities. So that so that's the same paper. So the sophisticated inference is sort of a nod to Bellman in the 21st century of belief-based schemes working under uncertainty in a formal way, whose appendix has the formal link to empowerment circa 2005.
Cool. Yeah. And you said that this quantity, this was an information gain quantity, it has a Bellman recursion, right?
Yeah, you can roll out into the future with effectively propagating your predictive posteriors into the future under different policies. So it's a little bit like you were working out what would be the empowerment with and without this action. So you're rolling out what would be. So you're rolling, and empowerment is an information theoretic functional of a belief distribution, and in this particular instance, it's a mutual information between the sequence of actions and the final state. But if you generalize that notion, what you've done basically is take a step towards modeling future beliefs, simply because you've worked out an information theoretic functional, or you're dealing with an information theory functional of probability distributions that you can treat as Bayesian beliefs under an MBP scheme in the future. So instead of rolling out sort of states that are likely to ensue under some fixed policy, some SARSA scheme or Q-learning, you're now actually rolling out beliefs. And of course, if you can measure the quality of beliefs in terms of empowerment, then you can now do this. You can now apply the sort of the Bellman trick, if you like, of doing the recursion. It's not, there's no temporal discounting, but you can still apply. In brief, what tends to happen is that as you roll out, if you heuristically, if I do that, what uncertainty will I resolve? What opportunities in terms of exploration will emerge? And furthermore, do I violate my constraints? And you score that in terms of the expected free energy. And if the expected free energy pursuing that path becomes incredibly costly, you don't explore that path. So it's sort of self-pruning as you go down a decision tree and roll out into the future. You don't have to worry about that because you're just jumping straight to the end. So you have a finite time horizon I think.
Right. Yeah, it's worth pointing out, like in my thesis, I basically showed that if you take a standard sort of Bellman equation and you just substitute empowerment gain in for reward, and then you just expand that recursion, you basically get a telescoping series where all of the intermediate empowerments cancel out along any path. So it basically just ends up being an initial to final empowerment difference because of this telescoping cancellation. So that kind of sounds familiar or similar to what you're saying.
That's interesting. This is I put this paper up first because you talked about the Bellman formulation. So this is actually making the same point, but in a much simpler way. When there is no uncertainty, this kind of belief-based probabilistic scheme can be formally shown to reduce to the Bellman optimality principle under Markov decision processes. So I think it's making the same point, but slightly more simply, that starting. So this as an early description of active inference and learning. And interestingly, I think perhaps I'm wrong, but does introduce something you mentioned before, which is if you can learn to what is enabling in terms of empowerment, then you don't always have to compute the empowerment, because that can be computationally quite difficult to do in high dimensional settings. From a behaviorist point of view or a psychological point of view, that basically means you're habitizing your epistemic empowerment. It's
like seeing a $20 bill on the ground. You're not going to think about the empowerment gain of making your bank account going up, but you just reflexively do it, right?
Absolutely. I'm not sure that this paper goes into it, but it is the companion paper will talk about those epistemic habits. But this is an early sort of just laying the groundwork for learning under these active inference schemes, but with a particular focus on how, when you take uncertainty off the table of the kind that would be entailed by measuring the empowerment, you get back to the Bellman optimality. So there's a section here just talking about the relationship to the Bellman formulations in terms of sort of epistemic foraging. Yeah. Again, this is really just for a paper trail, allowing you to tell a story from the point of view of this is active inference from Bellman optimality, and how that is a special case of this more belief-based scheme, and then moving on to what are the beliefs about, and then empowerment, and so on and so forth. Why you need to take several steps away from reinforcement learning to get the kind of scheme that you're interested in. I put this up just because I will be interested at some point in your appraisal of this in relation to the particular implementation that you introduced at the beginning in terms of the feasibility. So this paper, which is under peer review somewhere, but I can't remember where, basically takes the limiting case when a lot of your beliefs about the transition dynamics or the transition kernel are sufficiently precise to do reasonably precise rollouts into the future, raising the kernel to the power of whatever, and working out, can I get to my goal state from in the future from any given state by basically backwards induction, just using the same device as you were, but under constraints. So it did strike me that the way that you'd conceptualized the problem of finding paths through that were unconstrained to particular goal points had a lot of formal similarities to this slightly simpler implementation. It's simpler because we make the assumption that things are sufficiently precise. You can work with effectively logical tensors are replacing So basically, where there was 99% probability, you put a 1 in and 0 everywhere else in the transition kernels, and then you convert it into basically a logical induction problem, and then talk about the path of least action. What it doesn't have, though, and this is why I'd be interested in your take, is that it doesn't have an explicit representation of the probability distribution over Tor, or over the length of the path. The sort of the bound, the first passing, or the first crossing, or the first arrival, or dwell times. It may be implicit, but it's not explicit in this formulation. But it does have the same commitment to finding paths through, effectively like using backwards induction, but this is actually framed in terms of forward in reverse time, using a reverse time protocol, which physicists quite like. But it would be interesting to get your take on this kind of inductive inference. Is there an interesting graphic here? Which, so working out, can I get to my goal state from any other state, and basically providing constraints of the kind: if you go there, there is no route to your goal. Therefore, do not go there, but you can go there. So winnowing down in a way that allows you to, finally achieve your goal under constraints. Although I don't think that's been put there specifically. So that was really for my interest. If you at some point in the future, if there was an implicit or a way of connecting that to explicit distributions over the time taken, which is implicit in this but not explicit. So that's the thing I'd never seen before in your work, which I thought was really quite interesting. And certainly you can think about sort of first passing of time to absorbing states and the like, and dwell times, and the difference between absorbing and transient states, from that perspective, and putting measures on that, using that sort of the time distribution over time. I thought that was a very interesting thing. And finally, an endorsement of your factorization and the compositionality that you get by putting plans and policies into a non-Markovian scheme that is made non-Markovian by having this multiple factorization. Again, from the physicist's perspective, you could say it can't be any other way. Why? Well, because all our descriptions and generative models under which we operate as scientists, and certainly as physicists, rely upon a mean field approximation to our lived world. What is a mean field approximation? It is basically being able to carve nature at its joints by having multiple factors. So the factorization is really baked in to all of physics and all of the descriptions of physically self-organizing systems. And on that view, I think that you're basically appealing by putting the actions, associating the actions and the constraints that ensue from moving between different states within a particular factor, by isolating them in a conditionally independent way. You render what was completely intractable in terms of a massive joint distribution of into a set of very tractable conditionally independent states that you can deal with small tensors and little marginals over the constraint preferences. And I was struck with the formal similarity between some of your graphics and something that we've been looking at recently, which in this instance has been called a renormalizing generative model, for reasons I won't bother going into. But the key thing is basically having factors at different levels of the model that take not just the succession of states, but the paths that determine the policies, if that policy or sequence of action is controllable. It doesn't always have to be, but if it is controllable, you can now take it as a sort of generalized state at the next level, and then do your composition both in terms of factors, but also over time, so that your trajectories get longer and longer over time, which is something which is a canonical aspect of these deeply composed Markov decision processes, that you get a slowing down or a separation of temporal scales, in the sense that the dynamics or the number of transitions at one level is a deeper level is always smaller than the number of transitions at the lower level, so that the higher level can accumulate evidence for the path it has taken, whereas the lower level now receives some inductive priors or empirical priors or inductive biases from the level above. So again, in one sense, it has to be like that, and certainly your architecture had exactly that structure, and I don't think it can be any other way. And I think, you know, in one sense, you could say that, you know, there is no other way of doing it, and certainly, well, certainly if you were talking to physicists, they would applaud that particular commitment. Sorry, yeah, and what did I tell you what this paper was? Yeah, so this was focusing on a sort of a renormalization group approach to compositionality, and that's not what I'm using this paper as a vehicle, just to sort of pique your interest, but more the scale free over time to get dynamics, to break that, you know, to create non-Markovian or semi-Markovian belief structures or generative models by a separation of temporal scales, by having composition not just in terms of factors but also in terms of time as well. So it was that aspect of the scale freeness which was being celebrated in this. Oh, we've done that one. Good. Right. Yeah, that's all I had to say in terms of helpful links.
Yeah, that was very helpful. Thank you for that.
Fantastic. Thank you very much. So just a quick, as we come to an end, a quick another unmute and round of applause for the fantastic presentation today. Thank you very much, Tom, for joining us. That was brilliant.
Yeah,
thank you very much. Thank you very much, Carl, for the discussion afterwards. And thanks everyone for joining. We look forward to seeing you at the next talk, which will be on Monday by John Boyk. And until then, have a lovely afternoon. And actually, this is the first time we can do this. I'll just put because we have a YouTube channel now, I'll just put the YouTube channel into the messages if anyone wants to check this out. But yeah, thank you very much for joining, and have a lovely afternoon. Bye.
Thanks, everyone.
Thank you. Bye-bye.
Thanks, Carl. Bye.